sonraki konuşmacımız yurt dışından bağlantı yapacağız. Çok değerli bir araştırmacı. Profesör Stefano Pampanin is a full professor of structural engineering at Department of Structural and Geotechnical Engineering at the University of Roma, La Sapienza since 2015. He has been professor of structural design and earthquake engineering and chair of the Structural and Geotechnical Cluster at the University of Canterbury, Christchurch, New Zealand, where he joined in 2002 for 16 years. He has been president of the New Zealand Society for Earthquake Engineering. In 2017, he has been nominated Fellow of IPENS and Fellow of New Zealand Society for Earthquake Engineering. In the past 30 years, he has dedicated a significant effort in research, development, and design for low-damage seismic resilience solutions in concrete and timber, as well as for the seismic assessment and retrofit of existing structures, receiving a number of national and international awards. Following the 2010 and 11 Canterbury earthquakes, he has played active and key roles also as a president of NZSEE in the recovery and post-earthquake investigation and codification activities. Yes, Professor. Welcome. While you are connecting, we introduced you. Lately, we were also very inspired from his works in 2013 and 15 years. Thank you for coming here, and floor is yours.
Thank you very much to everyone. Can you hear me? Can you please confirm?
Yes, we are hearing you.
Excellent. So, first of all, thank you very much. I'm really pleased to be able to share a little bit of experience. 30 years of experience is quite a significant one, but the one that you people have been having in Turkey is equally important. I would have loved to be there. Unfortunately, I couldn't make it physically online, so I really thank very much the organizers, specifically Professor Erkan Yüksel, and all the Prekast Association of Turkish for this kind of invitation. I don't know, let me know if you're going to translate as I go, or if I'm going to stop.
Yes, already it's going on. Already translation is okay.
So let me move on right away to the presentation. So I should be able to share my screen. I hope it's going to work.
Yes.
So thank you, Ron, because I use the window, so I will not be able to see you. I just see a window and I will be speaking to that. Thank you very much for your patience. I know that it would have been easier to record, but it's so much more impactful to be able to speak to you real life. So this is a world map of what I would like to give you. A little bit of a summary of quite a number of years, 30 years. But if you see on the left-hand side, this technology probably dates back 3,000 years, 2,500 years. Depending on which country, the monolithic temples which were doing rocking could be considered. So everywhere in the world, people were using this sort of a technology as a seismic resistance. So we will be going in 30 years in a fast track summary from the concept of rocking from the Greek temples, you see over here, and that's the concept of what they were doing in the past, to the concept of controlled rocking, so using cables, post-tension cables. And by the way, marble is concrete. Marble is prefabricated. So there was a prefabrication in the past which was quite advanced, made of segmental construction. And what we've been doing in the last 30 years is to engineer that very good earthquake resisting structure by using vertical post-tensioning in the columns or in the walls, and horizontal post-tensioning in the beams. What is the novelty? The post-tensioning to be able to work as a spring, so as a controller spring, that they should be at least locally being unbonded, not bonded. And on the bottom side, you will see one of the buildings, which is probably even behind me as a screen, which has been co-designed and reconstructed in New Zealand. It's one of the latest low-damage technology as an iconic building for the Central Library after the major earthquake in 2010-2011. Professor Khan was asking me, can you please give a brief bio of yourself? And I was preparing a bio, then I sent a text, but the bio here is not really about the context, it's about a journey. And I would like to show you the journey of this technology using my story, because that has been basically my life. So the first 28 years in University of Pavia Milan, why is this connected, how is this connected to, linked to press technology? At University of Pavia with Professor Macchi, my mentor, I was working on rocking of the columns of the Leaning Tower of Pisa. So it was already looking at finite modeling and trying to understand how this mechanism can actually benefit. The rocking of the Leaning Tower, of the columns of the Leaning Towers, is actually a pure rocking. There is no control. At the Technical University of Milan, where I did my PhD, during my PhD I basically spent all my time, or as much as I could, working, having the honor to work with Professor Nigel Priestley at University of California, San Diego. That's where all started in terms of learning the ropes of precast seismic structure system, which is the press technology. Came back to Pavia for a couple of years at external lectures. I had the opportunity to go to New Zealand for 3 months, invited by Professor Park, informally, and more formally by John Berry, which was our technical engineer. The 3 months became 16 years. And over there we really pushed very much on developing further and further with several applications the technology itself. Where I'm calling now you from is from Italy, but not from Pavia anymore, it's from Rome. And so in the last 10 years in Italy we've been working on a combination of low damage with energy efficiency. Low damage for new design and energy efficiency for new design for retrofitting, excuse me, both for new design and for retrofitting of existing buildings. We are using low damage technology, and then we are combining with energy efficiency. Now, I assume, looking at your very interesting symposium, that during the 2 days, you have been going through the development of precast in seismic region, but I want to give a snapshot of what was the situation in the 1990s and what is typically the situation today. In the 1990s, the situation was not very different from now. The use of development of precast was limited. There was a lack of confidence on the performance, Northridge earthquake, precast car parking, industrial buildings, I'm sure in Turkey, but we know we had problems of car parking everywhere. So precast concrete industrial buildings everywhere. Unfortunately, 1999 earthquake in Turkey was a wake-up call for everyone. And there was a lack of seismic design code provision, a lack of university courses, a lack of information in the area of engineering and architecture. And the trend in codes, in major codes, US, Japan, New Zealand, and Europe, was typically to allow precast concrete only if you were doing an emulative approach, cast in situ approach, so a wet connection of the precast, semi-precast elements, or strong connection. What it is, we know very well. The hinged connection, as we could call it, is the typical precast industrial buildings as we were doing in the European environment, Southern Europe environment, and everywhere else in the world. It's a very, very strong, very efficient from gravity loading, not very good from seismic resistance. And we learned that. What are the advantages? Fast and quick. It's dry. It's fast. It's quality controlled. So we have, if we do a dry connection, we have all the benefits of the precast. Speed of erection, everything goes up as a Lego system. But if we have those connections being typically hinged with a couple of rods vertically, with a socket foundation, we have a very inefficient static schemes. So basically we have to over-design the foundation, over-design the column because they become cantilever. We need to limit the displacements, we need to limit the deformation. So the whole system under seismic region doesn't work very well. So we like dry connection, but we need a moment-resistant connection. So that's where, in the decades, emulative approach came into place. So because we needed a moment-resistant connection, there's been a lot of development of emulative approach. You know very well, because in Turkey you're doing very well, but I'm speaking about the world. The world, ex-Soviet Union, so we are talking about East Europe, there was already 1970s precast wet connection. New Zealand, 1990s, Bob Park et al., precast connection which are casted in situ in a wet in some regions. This is a publication on FIB by Fumio Watanabe showing that in Japan, but also approximately in all the many FIB countries, precast connection were casted into the core of the joint or in the midspan of the beam or somewhere far away from the beam. So we were having cruciform elements or beam supported on columns. Examples, we know very well double cruciform vertical in New Zealand, double cruciform horizontal in New Zealand with the wet connection over here. Emulative approach, this is from the FIB and we are referring to the Turkish, very good Turkish approach for precast concrete industrial buildings where there are wet connection instead of having only a dry connection. So all very good because we are giving a moment resistant connection, but how do they perform in a real earthquake? Well, they will perform as cast in situ concrete performs. So they will try to develop a plastic hinge, they will try to develop a mechanism for ductility in the wet connection or in the emulative connection itself. And we had, unfortunately, a very important experimental test that we didn't want to have in 2010-2011 in New Zealand. New Zealand, the Christchurch in New Zealand, the city was destroyed in the central building district by this major earthquake, especially the aftershock of 22nd February 2011. So we are 15 years after. 22nd of February 2026, in few weeks will become 15 years after. This is one of the best slides that I've been showing for years, literally for years, starting from the 1990s, to speak about the fantastic examples of prefabrication emulative that New Zealand was able to develop around the world for a 22-story building. This building went through the earthquake. How did it perform? It did exactly what it was meant to do. It developed a plastic hinge, so again it's a precast emulative approach, which is emulating cast in situ, is going to do a plastic hinge, is going to form a plastic hinge in the beam, is going to deform and provide ductility through damage. So by having ductility through damage, we are saving lives. So these plastic hinges were the sacrificial fuses of our building. But what was the consequence of it? So the consequence of it was to have a car crash test. So a building like a car crash test will deform plastically, and this means that we are not able to repair. So as a consequence of something that we can model the seismic car crash test, so people should very well know, or if they don't, we need to tell them that we are able to model the plastic hinge. This is the seismic design of the minimum by code in all the best codes around the world. What happened to that building and to many of other well-designed buildings according to a code, well-designed code, well-detailed plastic hinge? Those buildings had to be demolished because we did not know how to repair a plastic hinge. So let me go back. Precast is fantastic. Precast pre-stress can give you an excellent quality control, a speed of erection on long span. But in seismic region, we discovered that simply supported beams on columns, socket foundation alone, they are too flexible. We need moment resistance. Moment resistance can be provided by cast in situ, wet connection, emulative of precast connection. But once we get a real earthquake, we get to the same problem of cast in situ concrete, which is, we didn't know, which is developing a plastic hinge means that we are not able to repair it. So imagine the cost of a multi-story building like this, 40 million, sorry, this was actually an 80 million New Zealand dollars building. And it was not possible to repair it. So the loss is humongous. And if you have an insurance, that I know that in Turkey you're also developing, you might be fine, but you will not get with the insurance back your life. Not in the sense that you have been losing life, but in the sense that the comfort of your living will be completely destroyed. And that's the city. The city of Christchurch, completely underdeveloped, completely taken down by a controlled demolition, with 185 fatalities and 50 billion New Zealand dollars of cost, which means 30% of the gross domestic product. So after Canterbury earthquake, the new normal became safer, of course, but resilient. What does it mean, resilient? It means that we need to limit the impact, performance, drop, time. We need to limit the impact, and we need to be able to recover much more promptly. What is the way to do that? Is to go back to the past. And we go back to the ancestors. They had earthquakes, they developed temples, buildings, they were made in precast. It's not concrete, but it's very similar to concrete. There's no steel inside, so it's only acting as a rocking system. I have all the links that you can use for references of this video and explanation. This was becoming part of my, as I mentioned, the thesis on the rocking with finite element in the 1990s. And then the point is, can we learn from those technologies and use them in a new generation of low damage precast concrete technology? And that's what happened in 1999. So in the 1990s, the Precast Concrete Institute in United States, PCI, developed a new program, a big investment to launch, so revamp the use of precast concrete in seismic region. Because precast concrete was losing market. People were not happy with the performance of simply supported beams on columns, hollow cores, not properly detailed. The problem was not precast, the problem was detailing. The problem was connection. So this is an example, this is the end of the PRESS program. That's why we call it PRESS technology. PRESS stands for Precast Seismic Structural System, coordinated by Nigel Priestley. I had the honor that 26 years ago, is myself 26 kilograms ago, I joke all the time, and many years ago and many kg ago. And these are precast panels with vertical post tensioning, and these are frames with vertical post tensioning. Everything is unbonded. So how does it work? These are dry, jointed ductile connection. They are dry, they are not wet, they are using all advantages of having a prefabrication in a dry manner. They are using post tensioning to clamp the system against each other, and during the earthquake there is no breaking of the plastic hinge, but there is a rocking. There is a controlled rocking. Why controlled? Because the more you open the gap, the more the cables will stretch and push back. They are acting as a recentering springs. That can be done for beams and columns, for frame. That can be done for walls. And you will know, I hope, one of the most cited publication in the press technology in this environment, which is the Priestley et al. With Shri Sritaran, James Colley, and myself. I was a Fulbright visiting scholar at that time at UC San Diego, and these are the preliminary results of these 5-story precast concrete buildings, which worked outstandingly. If you want to know more about the story of that 5-story building, read the book. That's a big group of academics and engineers and colleagues and friends of Nigel Priestley prepared after his departure, because we wanted really to say how much he had impacted in the whole environment in terms of science, but also in terms of people. So a lot of people giving credits back. And in one of the papers, I was coordinating the story of the Press 5-story building, how it did happen, how we were working together with amazing teams, with John Stanton, Susie Nakaki, and so forth. And I think it will be very interesting to understand what was the evolution. So how does it work? If the traditional cast in situ or wet connection, emulative approach, will have to form a plastic hinge, and then we don't know how to repair it, or it's going to be very expensive to repair it, a renewed temple a rocking temple with the controlled post-tensioning and with the dissipation, will have a sort of what we call a flag shape. So it's going to open, dissipate through either bars, mild steels, bars internal or external type of dissipator. And so the new way is that in the past, in 1960s, thanks to Park and Paul in Priestley, we learned how not to allow buildings to collapse in a soft story because of the capacity design. So because of the column being bigger than the beam, because of shear being stronger than flexure, so there were a fuse in the plastic hinge in a flexure behavior. And so that was the famous theory of the chain. The theory of the chain of Tom Pauling saying there is a weakest link of the chain. The weakest link gives the strength to the chain. The force that you can pull a chain with, the capacity, is the weakest link. So if we design the weakest link where we want, then we will have a ductile behavior. But capacity design stands, the technology has improved. So the new technology allows us not to fail a building anymore, pre-70, not to have a plastic hinge anymore, post-70, but to have a rocking low damage solution which will not give an irreparable building anymore. So there is a new generation now, starting from the 60s, which was the major milestone in earthquake engineering. In the 90s, I would be calling that another major revolution, which is the next generation of. What did we do in this round the world map? In New Zealand, in Canterbury, in 16 years, I pushed a lot with my team. It was a fantastic environment, and we developed the next level up, a fuse which can be replaceable. If you leave the bars inside, then you don't know, after you heal them, you don't know how to repair them. So you can move the bar from the inside to the outside. And you can give to that bar a fuse type, a fuse shape. You can insert them into a anti-buckling restraint. Basically becomes a big BRB, buckling restraint brace, conceptually, which has a plate. In our case, we are using a simple rod, becomes small, small, small to become a small dissipator. We call it plug and play. I decide not to protect it, not to patent the solution. So I'm still a nice, happy, poor academic because I decided not to make any IP protection at one condition. Please use the name that we gave to this baby, technology baby. It's called Plug and Play. My name is Stefano. Please call me Stefano because my name has been given me by my parents. So please use it. It's free of charge. How much does it cost? 15 euros, 15 euros. We can manufacture in the lab everywhere in a very simple way. And this is giving you what? It's giving you the possibility to plug and play easily the dissipators in a socket, if you wish, at the bottom of the connection. They can become hysteretic, but you can use them viscous damper of different sorts. And the behavior of them is basically like you would be designing a fuse with the buckling restraint, with a cylinder, with a fuse, and then basically if you push it back and forth, you're going to have a very stable behavior. So they can become an architecture feature. Imagine your building that you've been already doing very well in Turkey. There can be the space to have some of them in some location around the building. So as it is easy to change a light bulb after anything that can break a light bulb, then it's easy to replace a plug and play. So the idea is earthquake engineering for a very simple implementation. People have been asking, I know that in Turkish you have been pushing a lot in 2018 with a code on Prekast, which would allow post-tensioning to be applied. Fantastic, thank you for doing that, it's great to know. Let's see what was happening in the past. 2004, the FIB bulletin, 2004, the bulletin that you can find 27, led by Bob Park and Fumio Watanabe, was already introducing the conceptual of press technology. In 2006, with Bob Park, I was in New Zealand, we managed to prepare the full code, a concrete code which is discussing about press technology. So the press technology can be developed in New Zealand code since 2006. And in Europe, you can use the New Zealand code. In the States, you can use the New Zealand code. In Japan, you can use the New Zealand code for alternative design. So then we develop a design handbook, so specifically for New Zealand design, but can be adopted, I'm using in my teaching for any other designs, where we were going step by step through the connection, through the calculation, and so forth. So we already said what is changing. We already said that, excuse me, these slides I should have taken away. What has been the novelty? The novelty is that in 15 years of work, we started working on the package. Not only the structural skeleton should be low damage, but the full facade, the full diaphragm, the full partitions. So the whole system should be low damage. So here we developed a final testing after 15 years on the shaking table in New Zealand, and I want to show you if it's working. Let me see, hopefully. The next slides, I will send it to you for you to see, and I will try to record it. You will see quite a number of experimental testing where we are able to see this rocking happening. It's absolutely, I can tell you, unbelievable. So when you see there is nothing happening, you are going to think like the trend people say, the journalists. They were coming to the shaking table test and they were saying nothing is happening. We are shaking the table, we are shaking using different techniques, and there's nothing happening. And I was saying that's exactly the point. There is shaking, but not destroying the building. They say, so what's the news? The news is that you are able to stay within your building after the earthquake without having to repair it. So, interestingly enough, people are expecting to have a seismic proof building, an earthquake proof. But when they see that, they are not believing that it can be done. So, the presentation is, and I'm closing, has a number of examples of real buildings that we designed and constructed in New Zealand. Multi-story building for offices, for the central library, for universities, and there is a plenty of application I'm showing around the world, including Costa Rica, including Turkey, including US, and so forth. And I'm showing the latest development, thank you to Birol from Maracali, who has been sharing some of the information about the post-tensioning solutions that they've been using. So, as a conclusion, after all these slides where you will see a lot of going on in terms of buildings and buildings and buildings around the world to show that it's possible, codes are there, the buildings can be done using this technology everywhere around the world. It's a matter of knowing how to. So it's a matter of forming engineers, educating engineers to do it. And that's what we've been doing in New Zealand, that's what we've been doing in Italy. And this is becoming the tricky part, because it's a catch-22, if I can. People don't know about it. Once they know, they don't know how to do it. Once they know how to do it, they think that it cannot be done because other people will not allow it to be done using the code. So there is quite a number of few steps. And I know that in Turkey, you have already developed the 2018 code Prekast, allowing post-tensioning to be done, so you're already advanced on that. In Italy, we are doing, we are slowly, a little bit slowly picking up. People are not aware, designers are not confident with that, so the code is there to allow that, but we need to do a little bit more, okay? I thank you again for this opportunity. Very sorry for not being able to show you the humongous amount of work, but I will send you also some papers, so summary of the slides, so you can appreciate that. Okay. So thank you, again, Professor Khan and all the people from the organizing committee.
We thank you. Thank you very much.